As the syllabus says, with our Rush 6-week gathering, quiz 1 tomorrow. Topic exclusively Chapter 17 considerations. Fair game stuff for the quiz relates to how far we get today. I haven't written the quiz yet. I write quizzes after I finish the lecture material, which corresponds to the fair game material. Same for exams. So I'll probably be here late tonight. I don't care. That's okay. Quiz will tee off right at the start of the discussion period. Wait. I got to tell some of you where to go. I'll post all of that on Sakai, the locations to which you go tomorrow. That's too confusing. Take a look at this stuff. I'll go get the information and let you know right now. Okay. In essence, there have been 3 discussion gatherings scheduled for Lee 104. Those all disappear. Period 1, section 4832, 4A32. That disappears. Everybody, period 1 tomorrow, you go to Lee 242. Period 2, 4A46 disappears. Everybody, period 2 tomorrow, goes to Lee 242. Period 3, 3 discussion classes scheduled. 2 will remain. The one in Lee 104 disappears. Period 3 is 4B14. That disappears. So if you're in period 3 discussion tomorrow, and you were originally scheduled for Lee 104, section 4B14. If your last name starts with letter A through M, you go to Lee 142. If instead your last name starts N through Z, you go to Lee 242. All the other discussion sections meet as scheduled. Any questions on this? I think it's pretty straightforward. Wonderful. Now, to repeat, our quizzes will start as a matter of practice at the start of the discussion class. So don't be late, because these are time limit activities. After 45 minutes, your papers will be collected on the discussion class quiz days. Your quiz papers will be collected by your discussion instructor, after which lesson plan will continue, just as if you were here in lecture class, except that you'll have a different presenter. Because in my discussion classes, my discussion instructors teach. Tomorrow, for those of you who wish to get on top of things, the material presented in discussion class will be Introduction to Chapter 18, Bronsted-Lowry Acid-Base Chemistry. Now, we also have lecture class tomorrow. That presents an interesting situation, because period 1, period 2, period 3, and period 4 gatherings all meet before lecture. So they will have had the Bronsted-Lowry acid-base stuff, introduction-wise. But period 6 won't have heard this yet. So period 6 is going to be a little bit off track, because in lecture I'll make a few remarks about the introductory considerations of Bronsted-Lowry acid-base chemistry, to at least try to be sure that the period 6 folks are in position to follow what we have to say, and then take off from that point of where the period 1, 2, 3, 4 classes got regarding their presentation. But nobody will be disenfranchised, and this is the way we'll operate. I don't have much of a choice, because once again, the people who run this university don't know what they do when they make schedules. They don't understand what's going on here. It doesn't matter to them about when the class meets. All they care is that it meets. And that's not good. So we'll do the best we can with what we have to see to it that everybody gets the same fair shake. Under no circumstances do I want students penalized because of scheduling difficulties or because of any goofs that I make. I hope you've seen the notice that I've put in the syllabus, which states, if in reviewing or studying you're looking at a past exam or past quiz, because there's a bushel of them there, and you see a question or problem which you think is wrong, please bring it to my attention, I make mistakes. Not because I want to, but I guess because I'm human. Same applies for any quiz or exam that we have. If after you've taken a quiz or exam, it is discovered that I've made a mistake, I'll have the quiz or exam regraded, rescored. I will not penalize you for mistakes that I make. But if I've made a mistake and I don't see it, and you don't report it to me, then you're going to be penalized for no good or fair reason. So I repeat again, if you think I've made a mistake, say so, and I'll take a look. Okay, on we go. As we were describing at the tail end of our gathering yesterday, we're going to take a look at a demonstration of equilibrium and how we can recognize when equilibrium is established. I've got two cylinders. Labeled A and B as they are in the notes. Cylinder A is 200 milliliters of water solution of a given quantity of dissolved potassium iodide. We don't care about the presence of potassium ion, but we want I- in there. I told you why yesterday. In order that you're able to visualize the dissolved iodine in the water phase, and to increase this, to do that, we have to increase the solubility of I2 in water. We put I- in the water phase for this two-phase liquid system demonstration we're going to do. To convert I2 to this triiodide ion. Because ions are fairly happy in aqueous media, because they are distinctly electric and water is also quite electric. In cylinder B, I again have a 200 milliliter water solution, iodine dissolved in this case, with the same amount of I- present in this solution as in this solution, at least initially. Because the concentration of I- in this solution is not the same as the concentration of I- in this solution. Do you see why? When I made these water solutions, I dissolved the same amount of potassium iodide. But in this system, the I- concentration is smaller than it is in this system. I- concentration. Why is that? Some of the I- got used up. Whoop. To react with I2 and make this ion. Now then, in flask A, I've got 200 milliliters of toluene. Lewis structure drawn for toluene over there, with an amount of iodine dissolved that's exactly equal to the amount of iodine dissolved in cylinder B. And in flask B, I got 200 milliliters of pure toluene. Now tell me, in which liquid, water or toluene, do you expect I2 to be considerably more soluble? In which one? Toluene. Why? Here's toluene. Oop. Did you see this structure in 2045? For those of you who saw this structure, what's its name? What's its name? Benzene. It's a benzene ring. Considered by many organic chemists to be the granddaddy, so to speak, of resonance. I think it can be said fairly so that the idea of resonance came to organic chemists when they first studied the unusual and interesting properties of benzene. You'll do this in organic class. And we'll do some of it later in this class. A resonance stabilized ring. Because at each carbon-carbon bond, what's the carbon-carbon bond order? You learn about bond order in 2045? Bond order is a numerical measure of bond strength. How do you determine bond order? You add the number, after you've written an acceptable Lewis structure, you add the number of bonding electron pairs at the bond sites which are under consideration. And then divide by the number of bond sites. How many bonding electron pairs under consideration for the benzene ring?
3.
How many bonding electron pairs? I'm listening. 9. The unfortunate implication, however, of a Lewis structure is that this is a single bond and this is a double bond. Double bond, single bond, double bond, single bond. Same statement applies here. Double bond, double bond, double bond, the rest are single bonds. Is that true? If we go to the laboratory with a sample of benzene and measure the carbon-carbon bond lengths, will they be different? The carbon-carbon double bond shorter and stronger than the carbon-carbon single bonds? Is that what we will find? No. What will we find? We'll find that the carbon-carbon bonds, regardless of which one we look at, they're all the same. The same length and strength. They're all shorter and stronger than a carbon-carbon single bond and longer and weaker than a carbon-carbon double bond. They're all the same. Well, what does that mean? That means, in reality, at each carbon-carbon bond site in the benzene ring, I've got partial pi bond character. Partial multiple bond character. And this is real. That's why resonance is so very important. But we have a problem when we try to represent this by drawing pictures. How the hell can I draw a picture of a part of a bond? I can't do that. Our model for a bond is a shared electron pair. You can write 2 dots, which I don't like because dots are messy. I'm up here living in a chalk maze. So I use sticks. Even for non-bonding pairs, I use sticks. Textbooks insist on dots for non-bonding pairs and sticks for bonding pairs. It doesn't matter, but I think it's more convenient to draw sticks. So when I have an electron pair to draw, if it's bonding or non-bonding, I don't give a damn. I'm going to use a stick. It's quicker, easier, neater to draw. So with 9 total bonds and 1, 2, 3, 4, 5, 6, count them, bond sites, what's the carbon-carbon bond order? Total bonds divided by number of bond sites. 1.5. How the hell can I draw a picture of a half a bond? I can't do that. But as a chemistry student, I have to know it. Now then, what do you think about the polarity of this molecule? Particularly polar? Yes or no? No. Now, as a consequence thereof, we recognize that I2 will demonstrate a far greater solubility in toluene than in water. Did you do any investigations on water solubility of I2 with your work in 45 laboratory? Yeah, you did, didn't you? You investigated the solubility of I2 in hexane, methylene chloride, water. In which of these 3 liquids did you find the I2 to be most soluble? Hint. If you don't remember anything about hexane, because I really didn't make an issue of its structure in 2045 lab, hexane has a ring structure like benzene. But hexane has strict carbon-carbon single bonds at each of its 6 carbon-carbon bond sites. So in hexane ring you have carbon-carbon single bonds, that's all. And to every carbon atom you have 2 hydrogen atoms attached. Now you may not realize it from these pictures, but here's a hydrogen atom, here's a hydrogen atom. Here's a hydrogen atom, here's a hydrogen atom, and here's a hydrogen atom. Here's a hydrogen atom, here's a hydrogen atom, hydrogen atom, hydrogen atom. Because in organic chemistry, the most common bond you see by far, besides carbon-carbon, is that of carbon-hydrogen. Hydrogen is by far the most common peripheral atom we know of. Well, I don't want to spend time writing all these H's all over the place. So the organic chemist saves time by doing this. Whenever you see a stick like this, it means at the end of the stick there's an H atom. No more, no less. Tell me, if I dissolve I2 in straight benzene rather than toluene, would the I2 be the same solubility? Or a little bit more or a little bit less? What do you think? If I dissolve I2 in straight benzene, that means you're looking at the same structure except you take away the CH3 group. Because if you take away the CH3 group, you now have a perfectly non-polar molecule, don't you? Whereas the toluene molecule, would you bet it's slightly polar? Not significantly so, but slightly polar. Because of this CH3 group, which is somewhat electronically different than the ring itself. So if I dissolve I2 in hexane, I should observe a greater solubility. What if I observe the solubility of I2 in carbon tetrachloride rather than toluene? If I tell you that when I dissolve I2 in a mixture of water and toluene, because that's what we're going to do, at equilibrium, I get a concentration ratio of I2 dissolved in toluene, I2 dissolved in water. These are molar concentrations of 70.0. What kind of a K value would I get? Let's call it K dist for distribution, because this K value represents the distribution of I2 as a solute in the two immiscible liquids, toluene and water. Relative to 70.0. What kind of K value would I get if I use carbon tetrachloride instead of toluene? What do you think? Same K value? Bigger K value? Smaller K value? I'm listening. I'm going to ask you about stuff like this tomorrow. I'll tell you that right now. Because one of the things I'm going to find out tomorrow is how much of the stuff in 2045 did you learn that you were supposed to have learned? The question is, how does the polarity of carbon tetrachloride compare to that of toluene? What can you tell me about the polarity of carbon tetrachloride? What's the geometry of carbon tetrachloride? What's the geometry? Tetrahedral. What's carbon central atom hybridization? Because I expect you to know this kind of stuff. Boom, straight away. That's 2045 stuff. And also 2045 lab stuff. What if I use methylene chloride, just like you did in 45 laboratory? You know that methylene chloride structurally is just like carbon tetrachloride? This has an sp3 hybridized carbon atom, and the general shape of this thing is tetrahedral, just like this. But this is a perfect tetrahedron. Is this a perfect tetrahedron? No. Why not? Why is this not a perfect tetrahedron? Are the chlorine atoms of the same electronegativity as hydrogen? No. Or are they the same size as hydrogen? No. Well then, what does this mean? Because that's the stuff you should have done in 2045, and then you'll understand what polarity and electronegativity mean. And if you didn't do it in 2045, you're going to do it now. That's what we want. We want you to understand chemistry. Okay? Would you agree from the sketch that I made of methylene chloride on the board that methylene chloride is fairly polar?
Yes.
Fairly polar? Well, will I2 be more soluble in the fairly polar methylene chloride? Or the less polar toluene? Or the non-polar benzene or hexane? I2 is going to be more soluble in the material of lowest polarity. And you can't get lower polarity than none. Now, let's ask one more question, just for fun. How do you think the chlorine-carbon-chlorine bond angle, how do you think this chlorine-carbon-chlorine bond angle, size-wise, compares to this bond angle? HCH. Now let me make a statement about this. The information presently contained in the 45 lab manual about issues like this is wrong. I have to fix it. And fix it I will. My suspicions were that since the chlorine atoms are a lot bigger than the hydrogen atoms, the van der Waals repulsions between the chlorine atoms would be certainly greater than the van der Waals repulsions between the hydrogen atoms. And that's correct. But my conclusion from that is wrong. My conclusion is that that would make the chlorine-carbon-chlorine bond angle a lot bigger than the hydrogen-carbon-hydrogen bond angle. Guess what? The HCH bond angle is the largest bond angle this molecule shows. What the hell's going on here?
The chlorine love each other, and they want to get close. They need each other.
I don't think so. Non-bonded atoms don't love each other because they each have electrons in their outer shell. Electrons all over the place except in the nucleus. And electrons which are not part and parcel of a bond do or do not attract each other. Coulomb. Do like-charged particles attract each other? Hell no. Now then, this is just a look-see at some of the fun stuff we're going to do this term. If you were a bonding pair at a CH bond site, would you be closer to hydrogen or carbon? If you're a CH bonding pair, are you closer to carbon or hydrogen?
Carbon.
Why?
Slightly more electronegative.
Because carbon is more electronegative. You learned about electronegativity in 2045, didn't you? Now let's put it to use. Let's make it come to life. Because electronegativity is a measure of the ability of a bound atom to attract valence electron density toward itself. And carbon is more electronegative than hydrogen. That brings the bonding pairs closer to carbon than they are to hydrogen at the CH bond sites. But how about the chlorine-carbon bonds? If you're a bonding electron pair here, you're going to be closer to carbon or chlorine? Chlorine, why? Because chlorine is more electronegative than carbon. That accounts for why this is a fairly polar molecule, because these bond dipoles are aimed like this, these bond dipoles are aimed like this, and so if you put these all together, you get a net bond moment, dipole moment for the molecule aiming in this direction. Now we'd have to resolve this with vector analysis and the like. Well, we're not going to go to that extent right now. Let's go back to the bond angle business. I've got two bonding electron pairs. I'll simulate these with dots so that you know what I'm talking about, okay? Here, centered close to carbon. Here, the bonding electron pairs are centered close to the chlorine atoms because of the difference in electronegativities. So between this pair, these two bonding electron pairs, between these two bonding electron pairs, where will you have the greater repulsion? Do bonding electron pairs like to be close to each other?
No.
Absolutely not. Because they constitute regions of negative charge density, don't they? And regions of negative charge density repel each other, don't they, Coulomb?
Yes.
So where am I going to have the greater repulsion?
HCH.
Between these electron pairs, which because of electronegativity wind up being a good deal closer to the central atom than the other two. What does that do? It opens up the bond angle. How about that? Isn't that neat? But it's all understandable on the basis of what you have supposedly learned by now. Now I know you didn't do any of that stuff in 2045, but damn it, you should. Because this kind of stuff is what makes these terms like electronegativity and polarity come to life. And we're going to do that all term, because we want this stuff to come to life. All right, finally and at long last, on with the demonstration. Since toluene is a less dense liquid than water, I've already placed the water in the cylinder so that when I add the toluene, in this case the toluene I2 solution, the toluene layer is on top. Same here. Now keep in mind, as we have told you, the composition of the contents of each cylinder, identical. Same amount of dissolved I2 in each, same amount of dissolved potassium iodide in each, 200 milliliters of toluene in each, and 200 milliliters of water in each. Identical systems. Are they at equilibrium? These systems?
Yes.
They're identical systems. Are these systems at equilibrium? I'm listening.
Yes.
This is an appeal to your horse sense. Given that the contents of these identical cylinders are identical, these systems cannot possibly be at equilibrium, because if they were, how would they compare visually? How would they compare visually? They'd look alike. Do they look alike? I don't think so. Now then, do you think if I stand here for a period of time equal to eternity that I'll get this to equilibrium? Get these systems to equilibrium? If I stand here for eternity, take kinetics out of the way, just look at it from a thermodynamic standpoint. We don't give a damn about time, so we'll take all the time we want. Because right now, the only way that the I2 can travel from the top layer, where it originally began, into the bottom layer is through this interface. So the rate of transfer has got to be proportional to the surface area of this interface. Same here, all the I2 started here. And the only way you can get to the top layer is through this interface. Do you already have evidence to support the conclusion that I2 is more soluble in toluene than it is in water? You remember we started here with all the I2 in the toluene layer and colorless water at the bottom. You see any color developing in the water layer? Just a trace of perhaps yellow? But over here, where we started with all the I2 in the water, you see a distinct pink in the toluene layer? It's showing you I2 prefers to be in the toluene layer because it's more soluble than the toluene layer. Hey, that's what this 70 value means. When I have these things at equilibrium, the molarity of I2 in toluene will be 70 times that of the molarity of I2 in water. That's what that thing means. Well, I don't want to wait for this transfer to take place strictly through this surface area, the analysis of which is offered you in the notes. I want to get these damn things to equilibrium right away. What can I do? What can I do to get these cylinders to have contents which are at equilibrium? Right away, quick. What can I do? Well, if we've reminded ourselves that the only place the I2 can go, top to bottom, bottom to top, is through this surface area, do you agree if I magnify the surface area, the rate of transfer will be more rapid?
Yes.
How can I magnify the surface area?
Shake it.
Shake them up! By golly, we're going to magnify the surface area tremendously if I shake them up. So let me get some wonderful and well-needed exercise. No, I can feel those fat molecules disappearing. Think we're going to get there? You betcha. Now we have equilibrium. The analysis of this from a rate standpoint is in the notes. But we're more interested right now by far in equilibrium. So let's proceed with this arithmetic. Oh, here we have. Okay. And say, if I do this experiment in accord with question 17.9, right here, using again toluene and water, and I start with 0.500 grams of I2. But for the liquid mixture described by question 17.9, I got 9 times the volume of water, as opposed to the equal volumes of toluene and water, which we combined in making our demonstration. 9 times more water than the toluene. Because I have 9 times more water than toluene regarding the mixture considered for question 17.9. When equilibrium is established, will I have more I2 in the water layer? For this mixture, where I got 9 times the volume of water, if I do this experiment, will I wind up with more I2 in the water layer than I have in the toluene layer because I got 9 times the volume of water? I'm listening. This is a simple arithmetic question. Got nothing to do with chemistry. Because I know you folks need practice with arithmetic. You've got to learn to think numbers. And if you're doing all your number thinking, so to speak, with that damn thing that has buttons on it, forget that. Now you're going to use this calculator to do arithmetic. The one that really is the best by far. I repeat the question. With this volume ratio, will I wind up with more I2 dissolved in the water layer? Yes or no?
Yes. Yes.
Like hell. Do you see that number? If I want the bulk of the I2 to dissolve in the water layer in mixing toluene with water, I have to have a volume of water which is more than 70 times than that of the water layer, of the toluene layer. The water layer has got to be more than 70 times the volume of the toluene layer. Well, that's what this means. Now, let's tackle the problem algebraically. Because we want to determine, as directed in the notes, the amount of I2 that will wind up in the toluene layer and the amount of I2 that will wind up in the water layer if we did this experiment. So let X represent the mass of I2 in the water layer. If that's the way I choose to define X, how will I define the mass of I2 in the toluene layer? Would you like to do this? Would you like to create a problem where you can write one equation and have 2 unknowns? Because if you do that, you're stuck. What's the proper way to define? What is that?
0.5 minus A.
0.500. That's better. You throw away the significant figures, you lose. I also have learned that from 2045, most students have no respect whatsoever for significant figures. So when you make significant figure errors on quizzes and exams, I'm going to charge you every time you do that. And so now we are ready to tackle the problem. Up top, we have the molarity of I2 and toluene. But here, My algebra approach is to consider the respective masses of I2 in the two different layers. If I have a mass of a substance like I2, but I want to express it as a concentration, given that concentration is a ratio of moles of solute, the dissolved stuff, per liter volume of the solution that contains the dissolved stuff. What information for the material do I have to put to use if I want a mole ratio instead of a mass ratio? What is it?
Volume.
For a given substance, if I want a mole ratio instead of a mass ratio, what property of the substance do I have to pay attention to?
Molar mass.
What is it?
Molar mass.
Formula mass or molar mass. Right? Aren't the units on formula mass grams per mole? Doesn't that immediately establish a relationship between mass and grams and moles of the stuff? Let the units talk to you. So I'm going to write mole I2 per FM. That's the formula mass in grams. Times, because up top we got I2 and toluene. 0.500 grams minus X. Because if this is in grams, and this is in grams, and this is moles, unit-wise these will cancel. And what's the volume of toluene in liters? 0.100. And so, in the denominator, I also have the inverted formula mass of I2 to convert mass to moles times the mass of I2 in the water layer, which I've expressed as X, contained in the volume in liters for the water layer. And lo and behold, I don't have to do anything arithmetically with the formula mass, inverted formula mass, do I? So here's my expression. How many unknowns? 1. Can you solve it? Yes. And if you solve it, before you do any arithmetic, how do you expect the value for X to compare to 0.500 grams? Before you do any arithmetic.
Smaller.
Do you expect it to be pretty close to 0.500? Of course it's got to be smaller. This isn't a mass manufacturing experiment. You expect X to be a number that's kind of close to 0.500 grams? You expect X to be a number that's a lot smaller than 0.500 grams?
Yes.
You're damn right. Because the I2 is 70 times more soluble in toluene than it is in water. Independent of the fact that it got 9 times as much water. And so if I do the arithmetic, I think I wrote the answer in the notes. I get that much I2 dissolved in the I2 layer at equilibrium. Now then, next page. Next page leads us into some analysis of chemistry equilibrium systems. Because this really did not involve any reactions. This is a physical equilibrium that we've looked at here. Now let's look at some chemical equilibria. Nitrogen reacting with hydrogen to make ammonia. Until now, I expect that the only formula you've seen for ammonia is NH3. A stupid formula. Because hydrogen is far less electronegative than nitrogen. And have you as yet become familiar with the formula for the species produced when the ammonia molecule gathers H+? What is that species? The ammonium ion. What's the formula for ammonium ion? H4N plus. Do you realize if you write a Lewis structure for the ammonium ion, you will see in fact that when H plus adds to ammonia, the formal charge which develops is on nitrogen? And if you write NH4 plus, what does that say the formal charge is? Doesn't say it's on nitrogen, does it? That's why that formula is no good. And we won't use it. Now, I know you're just getting used to this stuff. You see this crazy SOB up here barking and hollering and jumping up and down. So if you write NH4 plus, I'll say tisk tisk. You shouldn't have done that, but I won't charge you any credit. If you write OH minus, I'll say tisk tisk. You shouldn't have done that, but I won't charge you any credit. At least now. But 2 or 3 weeks later on, and if you're still doing that stuff, then I'm going to apply the one penalty that students always pay attention to. I'm going to take away student currency. You know what student currency is? Points! Right? We shall imagine to study this reaction system in a 1.0 liter flask. Now note, I like to consider equilibrium problems when we first introduce you to such, like now, with maintaining the arithmetic part of the puzzle as simple as possible, so I can get you to focus on the chemistry. And if I operate in a 1.0 liter volume system, then mole amounts and molar concentrations always compare how arithmetically?
Equivalent.
They're the same, aren't they? Because if I have a mole quantity and I divide it by 1 liter, have I changed the number? No. So let's imagine I have a 1.0 liter flask. And I place in this flask this quantity of nitrogen and this quantity of hydrogen with initially no ammonia present. I now establish conditions which will foster the reaction of nitrogen with hydrogen and begin conversion to ammonia. And find out that if for the conditions established, the reaction shuts down after I wind up with 0.190 moles of nitrogen, I can then answer the question, for this reaction system, at the conditions at which we've done this experiment, what's the value for the equilibrium constant? Well, here's the equilibrium constant expression. We've already talked about writing these. Now, it's usually the case that for gases we prefer to write equilibrium constant expressions in terms of partial pressures. But most of the equilibrium analyses that we're going to do will involve molar concentrations, because we're going to deal with water solutions of Bronsted-Lowry acids and bases and things like that all over the place. So let's keep it at concentration for now. That's why I've chosen to use a 1.0 liter flask for this consideration. Here's the K, written as a K sub C. What's a sub C mean? Concentration. If I write K sub P, that means I'm going to be looking at an equilibrium constant expression for gases, where the units will be atmospheres for each gas contained within, or atmospheres cubed. I mean squared if I got a 2 coefficient in front of the gas, or atmospheres cubed if I got a 3 coefficient in front of the gas. If I ask you right now, take a look at this. If I ask you to evaluate units for this equilibrium constant, what will the units be for the equilibrium constant? I'm listening.
1 over molarity squared.
1 over molarity squared. Do we see that? Because here's molarity squared, here's molarity, and here's molarity cubed. So it's molarity squared over molarity to the 4th. Doesn't that give me 1 over molarity squared? I'll ask you stuff like this tomorrow too. All right? Now then, let's get on with the analysis. This is in the notes, but please I ask that you follow along with our conversation rather than simply rely on the notes, to try to instill you with understanding. All right? I started with 0.200 moles of this. I wound up with 0.190 moles of this. How much ammonia did I make? Did you learn to read equations for reactions as stoichiometry guides in 2045? Here's our reaction equation. Defines the stoichiometry for the system. And without this reaction equation, you can't possibly wrestle with this. What's this reaction equation say? Do you know how to read reaction equations?
Yes.
This reaction equation says, if a mole of nitrogen combines completely with 3 moles of hydrogen, then I can make 2 moles of ammonia. It doesn't tell me how much I got. This reaction equation is a recipe. It doesn't know if I have any nitrogen or hydrogen or ammonia at all, period. So, I considered 0.200 moles of nitrogen, and after reaction I wound up with 0.190 moles of nitrogen. So how much nitrogen got used up? 0.010 moles of nitrogen got used up. Well, if 0.010 moles of nitrogen got used up, how many moles of ammonia did I make? 0.020. You agree with that? Because this thing tells me if I use a mole of this, I make 2 moles of that. So if I use 0.010 moles of this, I make 0.020 moles of this. So here I have this. And here I have this. What do I have for this? I started with 0.30 moles. How much of it did I use up?
0.030.
How much hydrogen did I use up? 0.030. Well, then how much hydrogen is left? 0.270. So let's put that in. And now at long last, I'll let you get out your calculators and push the appropriate buttons. And what do we come up with? Yep. Here's someplace. .11. Now then, tell me, if I choose to study this very same reaction system, but I choose to consider different quantities. Say, for example, I consider 2 moles, 6 moles, which if everything goes according to plan gives me 4 moles of product. If I wish to evaluate K for this very same reaction system, knowing that 0.11 corresponds to this equilibrium when the coefficient ratio is 1 to 3 to 2. This is for 1 to 3 to 2, this. But I want to evaluate K for the same reaction system after I've doubled the coefficients. What do I do? Will the resulting K for the coefficient doubled be the same?
Yes.
No. You have to square.
Will it be larger or smaller?
Larger.
Larger or smaller? Well, if I have to square 0.11, I'll be damned if I'm going to get a bigger number because I'm taking a fraction of a fraction. So the resulting K, which is 0.11 squared, is a smaller number, is it not? How about that? Now, what if I have the coefficients? Half a mole, 1.5 mole, 1 mole. Then what will I do to K? To get the K value, what will I do? Take the square root, won't I? If I take the square root of 0.11, do I get a bigger number or a smaller number? Bigger or smaller? Bigger. Bigger. Got to let these numbers talk to you. And now we take a look at this reaction. It's an important reaction because it corresponds to one way by which we can manufacture carbon monoxide, which, even though it's toxic, has a lot of industrial value. I direct you, please, to take a look at question 17.4 on page 1711. Because by now I expect you have read this stuff. And you've recognized that if I have a gas phase reaction like this is, and the coefficient ratio, pardon me, not coefficient ratio, but the moles of reactants as represented by the reaction equals the total number of moles of products, all gas phase, as represented by the reaction. 1 mole reactant gas, 1 mole reactant gas, 1 mole product gas, 1 mole product gas. Okay. How will the Kp and Kc values compare? Well, let's forget that and try it a different way. I'm going to put this thing in a piston cylinder apparatus. You know what a piston cylinder apparatus looks like. Will I have any effect on this reaction, right here? Will I have any effect on this reaction if it's at equilibrium and I have it in a piston cylinder apparatus and I increase the pressure? I reduce the volume by squeezing. Will I have any effect on this reaction by increasing the pressure? Yes or no?
Yes. Yes.
Do you know that reaction rates depend on concentrations of reactants, at least in most cases? And reverse reaction rates depend on concentrations of products. So if I got all these in a piston cylinder gadget and I increase, will I increase the concentrations of each of these by the same amount? So I'm going to affect equilibrium? No. How about this one? If I got this thing at equilibrium in a piston cylinder gadget and I squeeze, am I going to have an effect on this equilibrium? Yes. At the instant at which I apply the pressure, will the equilibrium be killed? Yes. You're damn right. Now what reaction will take place if the only change I've applied is to change pressure by increasing? What's going to happen to get me back to equilibrium? Is the thing going to go left to right or right to left? Which way will it go if I up the pressure? Will I go toward fewer moles or will I go toward more moles? Because if I up the pressure, look what I'm going to do to the concentrations of 4 moles of reactants versus the concentration of 2 moles reactants. Don't I have the greater impact on concentration change here? So it's going to go this way. But if I reduce the pressure, then it goes this way. All right? Now, what's that issue here? is the fact that water vapor, if water vapor is studied at temperatures that's pretty close to the boiling point temperature for water liquid, do you think water vapor will show a behavior describable by PV equals nRT? What is this PV equals nRT? This ideal gas equation. What's that mean? What conditions correspond to ideal behavior? You did this in 45. If I want a gas sample to behave in accord with PV equals nRT, what kind of conditions do I want the gas studied under? I'm listening. What conditions establish ideal behavior? I'm listening. You did this in 45. Or did all you do is to take numbers and shove it into PV equals nRT and not understand what the damned equation means? What conditions establish ideal behavior? The ideal behavior is established when interparticle attraction forces among and between the gas molecules don't mean anything. Will I have interparticle attraction forces mean something if the gas is warmed? Mean more something if the gas is warmed?
Yes.
Interparticle attraction forces? Tell me, if you want to get a liquid to become a gas, because in the gas phase, interparticle attraction forces are obviously the weakest for any sample of matter. If you're going to have condensation take place, interparticle attraction forces have got to control the behavior of the system. At home, if you want to take water liquid and turn it into water vapor, you put it in your freezer?
No.
What do you do?
Heat it up.
And if you heat it up, you increase the average kinetic energy of the particles in the system, don't you? And that defeats interparticle attraction forces, doesn't it? It wipes out hydrogen bonding, doesn't it? So one of the conditions you have to establish if you want ideal behavior is to heat the damn sample. What else?
Low pressure.
What about volume? Because the closer these particles are, the more likely interparticle attractions will matter. So you want high temperatures and low pressures to keep the particles far apart. So if I make the statement that I study this system at conditions at which water vapor shows a behavior that's describable by PV equals nRT, water vapor is behaving ideally. Can I rest assured that every other component of this system will also exhibit ideal behavior?
Yes.
Why?
Page bonding.
Do you recognize at a glance that the only material component of this reaction system which shows substantial intermolecular attraction forces is water? Because of hydrogen bonding? Hey, at normal laboratory temperature conditions, water is a liquid. We know that, at least mainly. How about carbon monoxide? Is that a liquid at normal laboratory temperature conditions? How about hydrogen gas? Whoop. This is carbon dioxide. How about carbon dioxide? Is that a liquid under normal laboratory conditions? No. Well then, the facts are screaming at you. The only component of this system which shows appreciable interparticle attraction forces is water. So if I've defeated the interparticle attraction forces of water because it's showing me ideal behavior, then the rest of them are guaranteed to behave ideally. Now I want to ask one more question about the next reaction system that you're asked to look at as we proceed through this analysis of different reaction systems and how they relate to equilibrium condition. NO2 reacting to become N2O4. The question is, because in 2045, you all talked about enthalpy and change in enthalpy. Remember that? When you measure the change in enthalpy for a reaction, what are you finding out about the nature of the products compared to the nature of the reactants? when you measure change in enthalpy for a reaction. Delta H. What are you finding out? Products versus reactants in their nature. What are you finding out? If you find that a reaction is exothermic, what can you say matter-of-factly about the products compared to the reactants for an exothermic reaction? Are they more stable or less stable? Do they have stronger bonds or weaker bonds? I'm listening. Stronger bonds. They're more stable. That's why the damn system liberated energy when it reacted. Hey, I get more stable when I lose energy. You put energy in me, I get less stable. Of course, you're probably looking at me now and saying, this guy's crazy, he's full of energy. So I ask a question. You see this reaction? Is this reaction guaranteed to be exo? Is it guaranteed to be endo? Or is it the case that as things stand, you cannot tell and you need more information?
Exo.
See that reaction? Is it guaranteed to be exo, guaranteed to be endo, or as things stand, you can't tell? That's three possibilities. Now, I'm going to ask you about this tomorrow because it follows from 2045. Guaranteed exo. Guaranteed endo. Can't tell. And most of you didn't vote, so that's 2,000 points off for tomorrow's quiz. For not voting! Because that means you're not participating, and I won't have that. Do you recognize that this reaction is strictly and exclusively bond forming? You're taking two of these molecules and turn them into one of these molecules every time this reaction proceeds at the microscopic level. So this baby is guaranteed exo. It has to be. And this is the kind of stuff you should know. Now, in addition to this, you see this directive here? You know about Lewis structures. I want you to write the Lewis structures for these molecules because I'm going to ask you questions about these Lewis structures tomorrow because it's part and parcel of 2045 and I need to find out what you know. Have at it.